I found this problem on Reddit physics homework, and I changed it up a little bit. But I've decided that there are some problems that are interesting or show some really cool points, and then those are the ones I'm going to do. I'm not going to do ones that I just think are dumb. I'm not going to do it. So let me describe this problem, and then there's a lot of stuff that we need to talk about. Two really big things we need to talk about, and it's going to be great. So the problem is this very long tube. I guess it's a tube. So it's a cylinder with a hole in the middle, and then and this, it's very, very long, and then this material in the inside has some uniform charge density rho. So the inner radius is A, the outer radius is B. That's that. So the question says, use Gauss's law to find the electric potential everywhere with respect to R equals 0. So that's that. And don't worry, I'm going to draw a better picture of this in just a second, but I want to show you that it is a three-dimensional object. Let's start with Gauss's law. So I'm going to write Gauss's law. Gauss's law says this. It looks bad, okay? And it can be bad, but we can use it to our advantage. Okay, that's Gauss's law. And you may be thinking, oh my gosh, what the heck? Integral with a circle. Not going to do that. Don't worry. We're not going to do complicated closed surface integrals of a vector field. That's what this is. We're going to do easy ones. So Gauss's law in introductory physics has to be done with something that has symmetry. So what this says, that if I find the flux, this is the electric flux around some closed surface, that has to be equal to the total charge inside of that closed surface divided by epsilon naught. So if you have, let's just say the simplest case, if I have a positive charge right there, and I can pick a shape to find the flux over which that has symmetry, and that's the key. If you don't have symmetry, you just have a hard problem. Okay, so I know that the electric field points radially outward from this charge, or I assume that to be true. And if that's the case, then if this sphere is centered on that charge, then the electric field on the surface of that sphere is always normal to the surface, because each one of these points has a little n hat, and these are all e's, right? Because this is e dot n hat. N hat is a vector, unit vector perpendicular to the surface, and then dA is the surface element. So in this case, I could easily find the flux, right? Because if I know that E is always in the direction of n hat, then E dot n hat is just the magnitude of E, and it doesn't change. It's constant over that surface, so I could factor that out. So I'd get this, E, the closed integral of dA. And that's just the integral, the surface area of a sphere, which is 4 pi r squared. You solve that, and you get the electric field due to a point charge, which seems silly, okay? Because it's like, hey, we already knew that. But this is a way to find the electric field for more complicated situations like this, okay? But the important thing here is that you have to know something about the field, or make an assumption about the field. I have to know something about the shape of the field, because this flux, electric field is a vector, but this flux around a closed surface is a scalar. Okay? And this is the charge inside. So let me show you two cases where Gauss's law works and you would not do that. Here is one. This is a dipole. Now if I do whatever surface you want, I could pick a sphere. And this says that the electric flux, if the total charge inside of this is 0, right? Because I have plus q and minus q. So the flux is 0. But that doesn't mean that the electric field is 0. And in fact, it's not. It just means that in some places the electric field's going this way, and in some places the electric field's going this way, and as I integrate around the whole thing, I get 0. So that doesn't really tell you anything about the electric field, right? Because I can't get some constant value out of that. And then here's the other one. I could have a positive charge, and then I could do this. I could do a cube around it. And again, I would get the same qn over epsilon naught. I'd get the same flux as that. But it doesn't tell me anything about the electric field, because over here, the electric field is different magnitude and different direction as over there. So when you sum around the whole cube, you get the same thing, but it doesn't tell you anything about the electric field. Is that okay? Okay, so let's do this. Let's assume that if this is infinitely long, then the electric field always points radially outward if it's a positive charge. So we're making an assumption about the field. Now we can find out something about the magnitude of that field using Gauss's law. Okay, but we have to choose an appropriate shape. If I choose a bad shape like this, I'm not going to get anything useful out of it. Okay, so let's choose a useful shape. So let's draw that cylinder, I guess it is, again. And let's just say this is my region with the charge. Okay, like that. So the first thing I want to do is define the electric field. So number one, I'm finding ER. I'm already assuming the direction. So all my magnitudes are pointing away from the radial direction away from it. I'm only finding the magnitude electric field. I'm actually not finding the electric field. And that's going to be okay. So I have three regions. We're going to need three shapes. This first shape is pretty easy. So if this is an infinitely long thing, I want to pick a cylinder in here with a radius r, and it's going to be a length L. Okay. So in that case, I could set up the integral E dot n hat, and yes, I said it's in the r direction, but I'm still doing it the right way, equals qn over epsilon naught. Okay. So right here, I can look at, in this case, I can say, well, what charge is inside of my little cylinder? What's in the middle of the wire? So there's no charge. So this is 0. So if the flux is 0 and the electric field is only in the radial direction, then the only way that could work is for E to be 0 newtons per coulomb, or volts per meter, whatever you want. Let's do volts per meter. That's the magnitude of the electric field. That's the only way this could work. Now, like I said, if you had a dipole in there, you'd get the flux is equal to 0. But we've already said that it's radial symmetry. So the only way it could be is to have a 0 magnitude. So in this first region, the electric field is 0. We'll call that E1. So this is region 1, 2, and 3. Okay, so now let's do this region inside the conductor. I should have brought another colored pen. I'm getting one. I got 2. Okay, so let's pick, again, if I say the electric field's radially outward, then I need to pick a surface that's easy to integrate. So again, I have this surface. It's a cylinder. This comes in and out of the paper, and it has a radius r and a length L. So it does have some length. It has some finite dimensions. Now, in this case, let me go ahead and draw my cylinder from the side. I think I need that. And I'm going to pretend like it's I don't know. So here's my Gaussian cylinder. So this has a radius of r. And then there's some electric field, E, 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 and this is the length L. So if I want to find the total flux, I actually have 3 surfaces. I have the side piece, which is if I roll it out, it has the area of a rectangle, and then I have these 2 end caps, which are circles. But on these end caps, n hat is that way. Over here, n hat is that way. Right there, n hat, these are n hats, those are e's, n hat, e, and so forth. So the surface is fine. N hat and e are in the same direction. On the end caps, e and n hat are perpendicular. So if I take the dot product on these end caps of e dot n hat, I get 0. There's no flux on these end caps because the electric field is this way, or that way, or that way, and the unit vector n hat's always on the side. So the end caps have no flux, and we don't have to worry about them. So now let's just look at the side, this whole thing. So I can say the flux of E dot n hat dA, it's not a closed, right? Because it's just the middle part of, I'd have to add the 2 zeros to make it closed. So in this case, that's going to be equal to the electric field E times the integral of dA. So what's the integral? If I integrate dA around the surface of a cylinder, I just get the side area of the cylinder. So this length all the way around is going to be 2 pi r, and then I need 2 pi r times L. So it's going to be 2 pi r L. That's the E, and that's the area, 2 pi r L. And that's going to be equal to the total charge inside, which I'll just write as Qn, over epsilon naught. And so look right here. This is the total charge, but this is the total charge inside. So it's only part of the whole thing. So I need to find, if I know the volume of that red stuff, then I could say Qn is the volume in, which doesn't really make sense, times rho. So what's the volume inside there? Well, Vn is going to be equal to the volume of this cylinder, the whole thing. I'm dealing with volume, not area now. So the volume of that's going to be the area of the end cap, which is pi r squared, times the length. And then I have to subtract out this whole, right? So I'm going to say minus pi a squared L. That's my volume. I can factor out a pi and an L, so I get pi L r squared minus a squared. So that's Vn. So now I have the whole thing. I can put it all together. I get E times 2 pi r L equals Qn, which is going to be rho times that pi L r squared minus a squared, all of that over epsilon naught. Now I can solve this for E, so we get some canceling here. The pi cancels, the L cancels, and I can solve for E. I get E equals rho r squared minus a squared over 2 epsilon naught. Now let's just check, right? Let's check a couple things. Number one, is this electric field at the boundary going to be equal to 0, right? Because I know right here the electric field is 0, so right there it should be 0 too. So if I put in r equals a, I get a squared minus a squared. I do get 0. That's good. Okay, what about the units? So if I have, remember that it should be something like, here's the electric field due to a point charge. The magnitude, E point, is 1 over 4 pi epsilon naught Q over r squared. So do I get Q over r squared? I'm not actually sure. So the okay, so rho is in the charge density. It's going to be coulombs per cubic meter. Oh, that's right. Ha, see, good thing I checked, because I didn't divide that side by r. Whew. See, checking things makes it useful. So this is coulombs per cubic meter. So let's put that over here. So it's going to be coulombs per cubic meter. Then I have meters squared on the top, minus meters squared. And then I have 2, and then I have epsilon naught. Let's just leave that epsilon naught, and then I have meters. So I'm going to get meters squared, meters cubed, just 1 meter, meter times meter. So I get coulombs per meter squared over epsilon naught. Same unit, so that's good. Okay. Now, you couldn't check what happens as it goes to infinity because you can't go to infinity in this because there's a boundary. Okay, so let's write down what we have so far. It is important. So I have E1 equals 0, and then E2 equals this thing, which right there. And this is a function of r. So it's rho r squared minus a squared over 2 epsilon naught r. And actually, you know, you could also write this as I could break this into 2 pieces. Rho r squared over 2 epsilon naught r minus rho a squared. Those look alike, but they're not. Over 2 epsilon naught r. And then here I have an r squared r, so that cancels. So it's going to be rho r over 2 epsilon naught minus a squared over 2 epsilon naught r, because that's r E2. Okay, so now I need to do the same thing. I'm going to go back over here. I need to find the electric field in the outside region over here. So again, we're going to make a cylinder. That seems obvious. Well, it's obvious to me. It's not obvious when you first do it. I mean, it really is not. And I apologize for saying that. So it has a radius of r again. But now you'll notice what happens. It doesn't matter how big I get. I'm going to have this finite amount of charge inside of that. It's still length L. Okay, so it's not the amount of charge is not going to change. But I do need to calculate that. So let's set up Gauss's law. So I have E dot n hat dA equals Qn over epsilon naught. So this is going to be the same thing. The end caps have 0, and this is the length L, and the side has constant E, so it's going to be E times the area of the side, which is 2 pi RL, and that's going to be Qn over epsilon naught, and that's also going to be rho times Vn over epsilon naught. So now if we have, here's our cylinder. So I want to find out how much charge is in there. I need to know the volume. It's just going to be the volume of the big cylinder minus the volume of the small cylinder times the length. Times the length. So this Vn is going to be equal to pi b squared times L minus pi a squared times L, or pi L b squared minus a squared. So I can put everything in. E 2 pi r L equals rho pi L b squared minus a squared over epsilon naught. And then the L's cancel, the pi cancels. I can divide by 2r, and I get E3 is rho b squared minus a squared over 2 epsilon naught r. And again, we can check the units. The units are going to work out again. But let's check out what happens as I get to this inner boundary right here. If r is equal to b, if that's the case, then I'm going to get a b squared over b, which is just b, right? So I will get this, right? So I'll get a term just like that. So let's write down E3. Rho b squared minus a squared over 2 epsilon naught r. So that in and of itself is a challenging problem, to find the magnitude of the electric field in those 3 different regions. And again, if you wanted to write these as a vector, you have to multiply them all by r hat to make them unit, to give them vector qualities. Okay, so now we want to find the electric potential. And we can define the electric potential. It comes from the definition of work done by a force, and we divide by the charge. And so you really get this. I mean, really, it's a change in potential. Delta V is negative the integral from point A, no, it's not going to, I say 1 to 2, of E dot dl. So this is a path integral now. So we've done a surface integral, now we need to do a path integral. But we're going to make it easy because E and dl are going to be in the same direction. The negative sign is because it was work, but then we moved to the other side of the energy equation to make it a potential energy, and then we divide it by charge to make it an electric potential, which is a terrible name. I admit that. And I didn't make it up, so it's not my fault. So since it's always a change, what we're going to do is to start at r equals 0. So at r equals 0, set V equals 0 volts. Again, another bad choice. Okay, that way we can do that. So let's just go ahead and integrate 3 times, and we can find our potential. So the first thing we need to know is that if, let's just say I'm on the outside, because I don't want to talk about the inside because it's weird. So here's our cylinder, and the electric field is radially outward. We know that. And if I move radially outward, then my dl is going to be equal to dr. The magnitude dl is dr. But more importantly, E dot dl, E is a vector, dl is a vector, it's just going to be E dr, right? So if E changes with r, I can replace that vector dot product with just E dr. And that's what I'm going to do. Okay, so let's do region 1. Delta V is going to be equal to negative r prime equals 0 to r prime equals a. And so I have a different integration variable than, my limits of integration are different. I'm just trying to be a good person, okay? And then the electric field inside region 1 is 0. So I get 0 dr. So when I integrate that, I get 0. Evaluate the limits, I get 0. So delta V is 0, or really, I'm going to say V is a function of r prime is equal to 0 in region 1. Okay, the electric field is 0, and you don't have to have the potential 0. It's just that the electric field is 0, the potential has to be constant. And so since we set electric potential as 0 at the middle, then it's constant 0. It's not 0 because the electric field is 0. It's constant because the electric field is 0, and 0 because we set V is equal to 0 at the center. Is that okay? You know, I don't know what to say if it's not okay. We're just going to have to keep moving on, right? Okay, so now we're in region 2. And so I want to do V. I'm going to actually write this as V as a function of r prime. It's going to be equal to negative the integral from r equals a to r equals r prime. Right? I'm going to integrate up to some point, and now find the potential at that point. So I can get potential as a function of r, of E dr. And this is actually E2. So if you go back over here, where the heck did I put it? E2. So let's write down E2. E2 equals, I'm going to use this form right here. If you notice something, you're like, hey, why did you break it up in those pieces? Because that's how I'm going to have to integrate it anyway. A little foresight there. Rho r over 2 epsilon naught minus a squared over 2 epsilon naught r. Okay. So that's my electric field. So now I just need to integrate, so I can say V of r prime is going to be equal to negative. Let's just integrate, then do the limits. So I actually have two integrals, right? Because I have two terms. So I'm going to say, let's do it like this. Negative, I'm going to pull out all the constants. Rho over 2 epsilon naught r dr. That looks easy. Okay. And then I get minus and negative, so I get plus. I'm going to pull the constants out. A squared over 2 epsilon naught, the integral of 1 over r dr. I mean, not impossible, but not. Okay, let's just integrate. So here I get negative rho over 2 epsilon naught. The integral of r is r squared over 2. So I get r squared over 2 from a to r prime. And then plus the integral of 1 over r is the natural log of r. So I get plus a squared over 2 epsilon naught ln of r from a to r prime. Okay, so now let's evaluate the limits. So I get minus rho over 2 epsilon naught r prime squared over 2 minus rho, I should have done that, over 2 epsilon naught a squared over 2 plus, now I'm going to have a difference in terms here with the natural log, but we don't like that, right? You can't take the natural log of meters, so instead I'm going to convert that into a ratio. So I'm going to write this, I'm just going to go ahead and write this as a squared over 2 epsilon naught natural log of r prime over a. So now it's a unitless quantity in there, and I can actually do the math. You can't take, like I said, you can't take the natural log of 5 meters. You can't do that. Okay. And that's V as a function of r prime. Now, I do need to check, right? Because what I'm really doing is continuing on with my other explanation, with my other values. So I might have to add in a constant or subtract a constant to make it work. I do know that at V of A, I want that to be equal to 0. And if it's not, I'm going to make it. Because I'm kind of adding up my potentials as I go along. So if I put in r prime as A, I get this term and that term. Oh, this should be plus. And they cancel and I get 0. And then I have A over A, and so I get 0. So it works. Okay, so we're all cool. We're cool here. Okay, now we need to do the other area. So we have region 1 is 0. Region 2 is this function. And then region 3, I need a piece of paper. Give me a piece of paper. and I need to rewrite my E3. E3 equals rho b squared minus a squared over 2 epsilon naught r. So I'm going to integrate v r prime is going to be the negative of the integral from b to r prime, right? Because I'm only in the region where r is greater than b. And I have this, I should have brought that out front, but that's okay. B squared minus a squared. I'm not going to separate those terms because it's just a constant. So it doesn't really matter in the integration. So now let's pull all that stuff out front. I get negative rho b squared minus a squared over 2 epsilon naught integral from b to r prime of 1 over r dr. So that's not too bad. V r prime is going to be equal to negative rho b squared minus a squared over 2 epsilon naught natural log, and now let's just go ahead and evaluate this, natural log of r prime over b. Now, here we do have a problem because I know that at v of b, I know what the potential has to be. It has to be what it was from the previous calculation. I have to use, this has to match up. Okay, so let's right here just say v of b. If I put in that, I get negative rho over 2 epsilon naught b squared over 2 plus rho a squared over 2 over, I have 2's, that's fine, 2 epsilon naught plus a squared over 2 epsilon naught natural log of b over a. That's the potential at b. And so when I go over here, when I put in this potential at b, it has to be equal to this. So let's set that equal. So let's add a constant right here if we need to. And then we can, oh, no, let's just add this to it, right? Because I know if I'm integrating up, then I just have to add this whole thing. So I just need to add this because that is VB. I don't need the constant. So V in region 3 of r prime is going to be this stuff, negative rho b squared minus a squared over 2 epsilon naught natural log r prime over b. And I'm just going to say this is all a constant, and I don't want to write it, even though it looks like I should get some cancellation. But I'm just going to say plus VB. And so there's my region 3. Here's my region 2. And then region 1 was 0. Right there. I already put a box around it. Okay, so, I could do this. It's a bad idea. There. Ta-da! And it only took me 28 minutes. That's a hard problem. I mean, it really is, because it involves a lot of different elements in it. You really have to understand Gauss' law. You really have to understand electric potential. And you have to integrate. You have to keep track of stuff. And I may have even made a mistake. I'm not saying I didn't make a mistake. Maybe I did on purpose. If I did make a mistake, maybe it was on purpose. And I want you to find it. But there you go. Hopefully that helps. If you're having trouble with that, it's okay. It's a hard problem.